So for the inverse rule, and like you said, Josh, yeah, there is a specific type that often shows up. They sort of look a little bit different each time, but they're very similar. They will, first let's talk about what is the inverse rule. The inverse rule says if you have two functions, f and g, that are inverses, the first thing we want to be able to know is that if f contains some point a, b, then that means that g is guaranteed to contain the point ba. That's effectively what an inverse function is, right? You exchange the x and the y values on. All right, so we know that that's true. And so the inverse rule tells us that if we are looking for f prime of a, that ought to equal 1 over g prime of b. Okay? So the derivative at a is equal to the reciprocal of the derivative of g, its inverse, at b, which is the y value for f of a. And so that's what the rule itself says. That's the rule that you need to know. And the way that the question is often worded, in fact, why don't I just, what I'm going to do is I'm going to go in and just grab one of the questions from one of those practice tests, and we'll just, we'll do a couple of them. I'll pull a couple different ones out. Give me 1 second to pull up. We'll start with 2012, and with any luck there'll be one. It's usually somewhere towards the end of the non-calculator multiple choice. Sometimes it's the last one, not that year though. Let's see here. All right, I found one here. And we're going to look at two different ways that we could do this one. This is one of the types that you'll sometimes see. So this is number 20 off of that 2012 test. So we got f of x is 2x plus 1 cubed, and g is the inverse of f. We know that f of 0 is 1. We want the value of g prime of 1. So what I would do if I were working through this problem is I would first write out that f contains the point 0, 1, which means that g contains the point 1, 0. And if I'm looking for g prime of 1, that would need to be 1 over f prime of 0. Does that make sense so far, Josh and everybody else?
Yes.
Cool. So for this particular one, we're given a function, f of x is 2x plus 1 to the third. All we need to do is figure out what f prime of x is and then evaluate it at 0, and we'll have our answer. So using the chain rule, that's 3 times 2x plus 1 squared times 2. And so if we evaluate that at 0, we got 3 times 1 times 2, which is 6. And so the answer here should be 1/6. Does that make sense? Everybody good there with that one?
Good.
Cool. Now, the other thing you could do, if they give you the function, you could go in and do this, y equals 2x, no, what was it? Was it 2x plus 1? 2x plus 1 cubed. And we could find the actual inverse function. We should know how to do that, right? It's x equals 2y plus 1 cubed, and then you solve. So you'd end up with the cube root of x is 2y plus 1, and you'd end up with y equals the cube root of x minus 1 all divided by 2. So effectively, this is 1/2 the cube root of x minus 1/2. And so this would be g of x. And so if we wanted to find g prime of 1, we'd take the derivative of this. Could do it this way. We have 1/2 times the derivative of x to the 1/3, which is 1/3 x to the negative 2/3. And then that's minus 0. So we'd end up with 1/6 of x to the negative 2/3. And when you evaluate that at x equals 1, because we wanted g prime of 1, that's 1/6 times 1 to the negative 2/3. 1 to the negative 2/3 is 1, and you get 1/6. So you could do that one by actually finding the inverse. So two different ways to go about that one. Now let's take a look real quick at, see if I can find one from the next year really quickly here. Should be able to. Let's see here. Yeah, here's another one. This one is similar to the one we just did. I'm going to do two different types. So I want to find one that has that's the other type also, but we'll do this one since I just found this one. So this is 2013. This is number 23. So G is the inverse of F, and 0, 1 is on F. We know 0, 1 is on F, which means that G contains 1, 0. And if we're looking for G prime of 1 and their inverses, G prime of 1 ought to be 1 over F prime of 0. And so F prime ought to be 2 plus e to the x, evaluated at 0, ought to give us 2 plus e to the 0, which is 2 plus 1. And so we should end up with G prime of 1 equals 1/3. This one, you have to use the rule because if you try to rewrite this as x equals 2y plus e to the y, you're going to have a heck of a time trying to solve that for y. You're not going to be able to do that. So you don't want to try and, when they give you inverses, you want to use the inverse rule. Does that make sense to everybody on that one too?
Yep.
Cool. All right, let's hope that 2014 has the other type. If it doesn't, I'm going to skip this one and go on to the one from 2015 and see if it does. Let me see here. I didn't see one going through here. Give me a second. I didn't see one in 2014. We'll try 2015. All right. One more try here. Maybe I'm just not seeing them, but. Okay, well, this is the next one I found is another one that's the same type, so that's not helpful. I don't know, I'm having trouble finding one that's like what I've seen also in the past, but sometimes they'll give you something where they say that F and G are inverses. I'm just going to make it up here. F and G are inverses, and they'll say, let's find F prime of 2, and then they'll give you a bunch of information. They'll say, all right, they'll say they'll say something like F of 3 is 4, and they'll say G of 3 is 2, and they'll say F prime of 3 is 8, and they'll say G prime of 4 is 6, and G prime of 3 is 7. And, all kinds of nonsense stuff here. F of 4 is 1, and, all kinds of stuff like this. So they'll give you a bunch of information like this. And they will ask you just about one specific value for F prime. And so what you need to do is you need to recognize that F, if we're looking for F prime of 2, must have a point 2 comma something. And that tells us that G needs to have a point something comma 2. And so we'll look at all the values that they gave us and say, here is where G equals 2 and it's 3. Okay? And so that tells us that F has the point 2, 3 and G has the point 3, 2. And so that tells us then that F prime of 2 should be equal to 1 over G prime of 3. And then they'll just have given you the value. You just need to know, you'll just have to have used the inverse rule to determine that you need to know the value of G prime of 3, not the value of F prime of 3 or G prime of 4 or whatever else. You just need to know G prime of 3 and they give you that 7, so it's 1, 7. So they do like to put those ones on there. Those have been on. I know there's one like that on, I think it's on the 2008 test that's in there. I just didn't pull that one up, but that also shows up fairly often. Does that make sense? Is that helpful with the inverse rule for everybody?
Yes.
Wonderful. Other questions?
This is just like a general question, but for the second derivative test, when you're looking for like a min-max, would you use that like as like a last resort when like a sign chart doesn't work? Because I know we had a problem with that before where we used the second derivative test.
Yeah, so yes, it can be a last resort if needed. Couple things to remember about that. First off, and I'll talk about this for like 2 or 3 minutes here, so I'll answer everything you want to know about it. On the second derivative test, first off, it only works, and this is important because some people will try to do the second derivative test when f prime is undefined. It only works if f prime is 0. And so that's an important thing. If f prime is undefined, it's still a critical value. It could still be a max or a min, but the second derivative test will not work. So second derivative test just says that if f prime equals 0 and f we'll say at x equals c, f prime equals 0 and f double prime is negative, that tells us the function is concave down, which tells us we have a max. And at x equals, we'll say max at x equals c. And if at x equals, I don't know, b, f prime is 0 and f double prime is greater than 0, it tells us the function is concave up. It tells us we have a min at b. All right, so just so everybody is clear on what the second derivative test is. Now, reasons to use the second derivative test. One, if the second derivative is really easy to take. So like if you were given, like a cubic or something, y equals 3x squared minus, I don't know, minus 5. That's not a cubic. 3x cubed minus 5x plus 1, let's say, right? And 9x squared minus 5, and you end up with, when you take your derivative, right? And you end up with x equals, that equals 0 when x is positive or negative square root of 5/9. I mean, personally, if it were me, I think it's just as easy to go in and say y double prime is 18x. And so when I have the positive square root, then, so at root 5/9, we're going to have a positive value for our second derivative, which tells us we're going to have a min. And at negative root 5/9, we're going to have a negative value, which is going to give us a max. So sometimes it's just convenient to use it because the second derivative is super easy to take and evaluate at there. And you might want to use it if, if the values that you're getting here are sort of annoying and you're not sure what values might be to the right or to the left of them for your sign chart, because you got like, square roots of fractions for multiple different things on the sign chart, and it's just a little confusing. It might be easier to use the second derivative test. But the second derivative test is also really important for problems like this. Give me like 2 seconds. I'm going to see if I can find one real quick where you would have to use it. Otherwise, I'll make one up. But there's a specific type of question that they sometimes throw at people. And I want to say they usually show up in the calculator section, even though there's no need to have a calculator for them. That's a good problem, but it's not the one I want. Yeah, I don't see one right off the bat. So that's fine. I'll just make one up. They'll give you something like, here are values of x, f of x. They probably won't even give you f of x. So here's values of x, f prime, and f double prime of x. And actually, they probably would give you f of x also. So let's say we got x, we got f of x, and we got f prime of x. And let's say, we got values of 1, 2, 3, 4. And let's just say that here at x equals 2, f prime is equal to 0. We got a negative 1 here. We got a 3 here. We'll put a I don't know, 5, 6. These don't, I don't know why I put those. Those don't really matter. Put in another 0 here. We'll put in something like 2 there, and we'll put in let's put a 0 there, and a negative 1 here, and a positive 3 here. All right, so I'll give you some chart like this. And then they may ask, sometimes they'll ask like all kinds of different questions. It'll be like, which of these is true? And they'll give you like 1, 2, 3, all kinds of different things that you need to like try and figure out about this chart. But the reason why the second derivative test becomes really important on charts like this is because if they ask you about what's going on at x equals 2, your first instinct is to look probably at f prime and say, f prime is 0, which tells me that I might have a min or a max, right? Everybody would agree with that, I hope?
Yeah.
Potentially. Potentially it's a min or a max, right? And so then our first instinct, because what we normally do is we make a sign chart, and we say we look to the left and we look to the right, and we say, okay, well, to the left it was negative 1, which tells us it was decreasing, and to the right it was 3, which tells us it was increasing. And I would say that most, maybe not most, but people that aren't, haven't done a problem like this and aren't being extra careful about it might come up and say that we have a min there. True? It sure looks like it. Negative 1, 3, decreasing, increasing. Yeah. The problem with that is we only know that it's decreasing at 1, and we know that it's increasing at 3. But that doesn't mean that it might have had another max or a min in between 1 and 2, or 2 and 3. It might have gone decreasing and then had a min, let's say at 1.5, and then increased, and then had a max at 2, and then decreased, and had a min at 2.5, and then increased again, so that at 3 it was increasing. You guys all see that? That conceptually makes sense. That's why a sign chart sort of fails in this instance with a chart of values.
Yeah.
Yeah, and so the only way we can be guaranteed about what's going on here is by looking at the second derivative, using the second derivative test. So since f prime was 0 at x equals 2, we're guaranteed that since the function is concave down at 2, that we must have had a max at x equals 2, even though the f prime values are there in this, with negative and positive to sort of trick us. And they will try to trick you like that. They will ask, can't guarantee it, but it's quite possible that they will try to trick you like that and say, all right, here's your chart. What's going on at x equals 2? Is it a max? Is it a min? Is it a point of inflection? Whatever. They'll give you a bunch of different choices. And a lot of people will go, it's a min. Negative, positive, 0. Yep, it's a min. But no, it is 100% guaranteed to be a max because of the second derivative. And so we could do the same thing. They might ask you what's going on at 4, and you'd be like, well, at 4, I don't know. It was increasing before I got to 4, we think, but I don't know what's going on after 4. Well, that doesn't matter. I know what's going on at 4, right? It was f prime was 0 and f double prime was 3, and so therefore we had a local min. Does that make sense? Does that answer your question? That's like the main time what I would see that you want to use it. The other example would be like what we did do in class, where you've got a second derivative, or sorry, you got an implicit derivative. And so when you have your implicit derivative, sometimes it's really hard to determine, if you're trying to choose an x value to the right or to the left, the y value is also part of that. So you need to take a second derivative to evaluate it, what it is there. Does that make sense? Does that help?
Yeah, that actually helps a lot. Thank you.
Yeah. And then another thing to be careful about is, you're looking at x equals 3. This is unrelated to the max min second derivative test stuff, but let's look at what's going on at x equals 3. It looks like it could be a point of inflection, right? Because at x equals 3, f double prime is 0, right? Which indicates that it's potentially a point of inflection. And it looks like to the left, it's concave down, and to the right, it's concave up. So we think that seems like it should be a point of inflection. But the same thing that was going on here, where we weren't sure what's going on between 1 and 2 and what's going on between 2 and 3 also applies. This function is not guaranteed. I would say not for sure. Right? It's not guaranteed that there's a point of inflection at 3. It looks like it was concave down. It was concave up. It did change concavity between 2 and 4, but that doesn't mean that there was a point of inflection at 3, right? The second derivative sign chart could potentially look, like this. Here's 2, here's 2.5, here's 3, here's 4. It could be, negative from 2 to 2.5, positive from 2.5 to 3, 0 at 3, and then positive again from 3 to 4. And that would totally match up with what we've got here. We just didn't have the information at 2.5. So we can't guarantee that there's a point of inflection. So same idea, same concept. They will try to trick you on that. And you got to be careful with the wording on those multiple choice questions, especially when they're giving you all these different things that you got to check. Usually they'll say, which of the following is guaranteed to be true, or is definitely true, or is certain to be true. And so just because it could be a point of inflection there doesn't guarantee that it is. Everybody good with that? Hopefully that's helpful. Just something to sort of look out for and be careful about on the test. Other questions?
Could you go over part D of page 15 of the miscellaneous FRQs?
Yes. Let's see here. You'll have to tell me what it is again in a second once I get the document open. All right, miscellaneous FRQs, you said page 15?
Yes, page 15.
Part D, correct?
Yes.
All right. Oh yeah, that's a good one. If we need to, I can pull out the scoring guidelines in a minute and we can look at the point values on this if you guys want to. So we've got f prime of 5 is 3, f double prime is negative for all x between 5 and 8. We want to use the tangent line of the graph at f, tangent line of the graph of f at x equals 5, and the secant line for the graph of f between 5 and 8 to show a couple of different things. So the way we will do that is, first off, we need to get a tangent line for f, which you may have done earlier. No, it doesn't look like you did earlier. So use the tangent line for f at 5. So that would be the point 5, comma, -2. And f prime of 5 is 3, so a slope of 3. So we would say that the tangent line is y minus -2, or y plus 2, equals 3 times x minus 5. And we are using, sorry,
You can't see what you're writing.
Oh, huh. I forgot to share the new screen. Sorry. Okay. That'll be better now for everybody, now that they can see the problem, huh? Okay, so they gave us a chart. They're asking us here, part D, supposing that f prime of 5 is 3, so that's why I put a slope of 3. F double prime is negative, which tells us that this function is concave down between 5 and 8. And then we want to use the tangent line to f at 5 to do some stuff with f of 7. So the point was 5, -2 from the chart. The slope was 3 from what they gave us. Y minus -2 equals 3 times x minus 5. And so because we're using a tangent line and the function is concave down, right, on this interval, it's concave, that's atrocious. Let's just draw that all again. It's concave down. And I've used the tangent line at 5. What does that tell you about the value you would get if you evaluated this at x equals 7? Well, let's suppose this is 5. This is x equals 5. And here is, I'm going to do it in a different color. Here is x equals 7. Well, I'm using the tangent line as an approximation for the function. Right, so y plus 2 equals 3 times 7 minus 5 gives us y is equal to what? Should be 4, right? Which makes sense because they want us to show that f of 7 is less than 4. And this is our function f of x, right? The value of f of 7 is less than the tangent line approximation of f at 7. Does that make sense? Why that's why it's this tangent line is proving that f of 7 is less than or equal to 4?
Yeah, so because the function is concave down, the tangent line approximation is an overestimate. And
Correct.
so, okay.
Yep. And so the true value is less than the value we get from the estimate. Now, we'll do the work for the secant line in a second, but let's, we know what a secant line is, right? A secant line between 5 and 8, here's x equals 8. What's the secant line? It's just a line through those 2 points, right? Pretend that's actually looks like a straight line. Well, if we're talking about at 7, this value down here, this is our secant line approximation of f at 7. And so what can you tell me about the secant line approximation anytime the function is concave down? Sure looks like it should be below the true value, right? So for a concave down function, the tangent line approximation is greater than the true value, which is greater than the secant line approximation. So we just need to write the equation of that secant line through 5, x equals 5 and x equals 8. So that would be f of 8 minus f of 5 over 8 minus 5 to find the slope. Now f of 8 was 3. 3 minus -2, that would be 3 plus 2 is 5 over 3. So we would then say that the secant line's equation ought to be y minus, and you can choose either one. You can choose 5 -2, or you can choose 8, 3. I'll just say y minus 3 equals 5/3 times x minus 8. And if we're going to use this to approximate the value at 7, then we're going to have y minus 3 equals -5/3, or y is equal to 9/3 minus 5/3 is 4/3. And so the secant line approximation is 4/3, and the true value of the function then must be more than 4/3 because the function was concave down. And this is one of the things that I have written up. It's definitely written up in the A/B test reminder thing in Google Classroom, which I'm going to remind you all about and show you where it is again in a second. But for a concave down function, secant line is less than the true value, tangent line is more than the true value. And drawing the little picture like that, I think, definitely helps. And if the function was concave up, if it's a concave up function, well, then the tangent line, if I'm using the tangent line at some point to approximate some other value, the tangent line will be less than it. And if I'm using the secant line through that point on a concave up function, let's say we're trying to approximate the value here, right? The secant line will be more than the true value, and the tangent line will be less than the true value. Does that make sense?
Yes. So like for that problem, would you have to explain like the function is concave down, so the tangent line approximation is going to be greater than, or would just showing?
Yeah, you need to explain it. You need to say that. Yep. Yep. But just, I mean, that one sentence is all you need for, you do one sentence. The function is concave down from 5 to 8. So any approximation from the tangent line is going to be greater than the true value, and any approximation from the secant line will be less than the true value. Good enough. That's all the explanation. Then you do a little bit of work to show that the approximation using 5 with the tangent line was 4, which is why f of 7 is less than 4. And then you show the work up here to show 4/3 was the secant line approximation. Cool. All right. Anybody else have any quick questions? Otherwise, I'm going to show you guys a couple things in Google Classroom that have been up there a while, but you may not have looked at if you weren't taking the May 4th test. And then we'll be good for today. All right. So we're going into Google Classroom here, period 6, right? So down here, first thing, just make sure you've looked at this, right? We've got the extra review session here tomorrow, right? Tomorrow from 5 to 7. That's the right time, right? That's what I said. Yeah, tomorrow 5 to 7. And then first 2 videos are me going through literally everything that we did this year in about 3.5 hours. There might be some extra stuff at the end of the second one that's not me just reviewing the basic stuff. I'm doing some specific problems or something. But definitely, if you're taking the May 24th test, watch these 2 videos this weekend. If you have questions on them, let me know. Bring those questions on Saturday from 5 to 7. And then the other thing is, let's see here, these 3 documents down here a little bit further. So the AB calculus stuff you must know, just make sure you know all this stuff. There's some exam tips. These 2 documents I did not create myself, but they have good information in them, and it's all stuff you should know. I will go through some specifics about the exam tips on Saturday during the review session. And then we also have this other document called AB test reminders, which I'm hoping you've opened and taken a look at. This one I did put together. So this just has all the reminders that you might need for anything. So like stuff between a function and its derivative, a function and its second derivative, how all 3 of those things are related on graphs, when to use parentheses, when to use brackets, those kinds of things. All the information about different approximations, when they're overestimates, when they're underestimates, how to do all that kind of stuff. When a trapezoidal is an under or an overestimate. Same thing I was just talking about, using the tangent line, the secant line, like that problem we were just working through, like all that information about that one is here, right? L'Hopital's rule, the linearization formula, important stuff. Usually in the, and I'm going to talk about this one real quick. Usually in the multiple choice, there is a question where, let's see here. I know it's in here. There it is, where you have to convert between an integral and turn it into the limit notation with the summation. And so these are the 2 formulas that you need to know to be able to do that. There's almost always one of those in the multiple choice. So You can get the delta x value by just doing b minus a over n. You can get the x sub k value by doing a, the lower limit, plus k delta x, and then just plug that x sub k into your function, attach your b minus a over n to the end, and make sure you get your limit and your summation. So just things to look over, things to know, limits you need to know, all that good stuff. So I think that's a good thing for you guys to read over and look over a couple times this weekend as well.